Looks like some people are finishing up, so feel free to, so you don't want to meditate on this. Usually you like to ruminate. Looks good, nice, good job. Look good, wasn't too hard. I'll try to keep them easy for the exam. Are those the same type of writing utensil?
Yeah.
You just, okay, gotcha. Looks okay. All right. Stack it up. Very nice. Gotcha. Well done. Is this homework? It didn't get put in with the other batch? I'll take care of it. There. You're happy with that? Good job. Let me stick this in the stack. All right, if you're just finishing up, try to wrap things up. I'm going to come get what you have and then staple it all together. Good. Did I get yours? Oh, you've got one you're going to keep as a souvenir? Yeah, that's fine. I know, it's, you could do your notes on that little piece of paper. All right. Yeah, take your time, but try to hurry up. All right, you're all set. Good job. Okay, excellent. All right, well, let's take a peek at this. There we go, good. Take a peek at what I did. Hopefully I didn't scan yours, so I don't know if I got it right. Sometimes I find I might make a mistake, but we'll find out. So first things first, I took the initial value y of 0 is equal to 7, stuck it in there for, so in other words, t is equal to 0, y is equal to 7. I got this, so t equals 0, y equals 7. Look good? And then I took the derivative, which I didn't write down, but I knew what it would be. It would be c1 e to the t minus c2 e to the negative t plus 2t. So I plugged 0 into that, and I got c1 plus c2. And then, oh, sorry, it's down there. Or sorry, it would be c1 minus c2. That should equal 3. So that's from the derivative. And then you're just solving two equations, two unknowns. However you want to do it, I don't care. You want to do it the hard way? Fine. I'm going to do it the easy way. Elimination. Let's just write these like this. Add those together. You get 2c1 is equal to 8, which means c1 equals 4. And then it's an easy thing to realize that c2 is equal to 1. And then the final answer is that this is the particular solution we're interested in. Notice that I've taken my c1 and my c2, and they are in there. Look okay? Did I get it right? Okay, at least some of you say it's the, so hopefully I did get it right. Okay, now we're skipping a section 1.3, sad, isn't it? Well, the reason is that in the past, I've started out with section 1.3, and then I get people dropping the class. They're scared. Because 1.3 is applications. It's like, what are we doing with differential equations? I'll tell you one because it has something to do with what we're doing today. And that is Newton's law of cooling. You know Newton's law of cooling, maybe you don't. Newton's law of cooling says that if you have a mug of hot liquid, that hot liquid will decrease in temperature. It will cool at a rate proportional to how far it is away from room temperature. So if the room is 70 degrees Fahrenheit and the liquid is 200 degrees Fahrenheit, it will cool rapidly, whereas if the room is 70 and the liquid is 100, it cools much more slowly. So the way we would write this is something like this. Let's let T, and I apologize for the fact that we're going to have two T's here. Maybe I'll label them. T is temperature. Temperature. And little t is time. How's that? So we have the two T's there. Sorry about that. But here's the interesting thing is that if you take Newton's law of cooling, it says that the rate of change of temperature with respect to time will be proportional to the difference between the temperature and the ambient temperature. And so in order to avoid an additional T here, which most of the time you put T sub zero, I'll just say 70 degrees, and we'll go with Fahrenheit, which I know is very American of me, but sorry. But anyway, so this is just an example. I just wanted to show you an example is that we have the change in temperature with respect to time is equal to some constant, which could be determined based on several factors, times the temperature of the object minus the ambient temperature. That's it. So that's a differential equation. That's an application from real life. And we can actually observe this. You can go get your mug if you have like a meat thermometer, that like a digital meat thermometer that will, you could take temperature readings every minute. Oh, I should do that. I could do that. Maybe Monday. I'll bring in my meat thermometer and we can have fun. But anyway, we could take temperature readings and watch as the thing declines, and we can solve this differential equation. Okay, what we're going to do today is we're going to solve differential equations without actually solving them. What I mean by that is if we have an initial condition, for example, if I know that the original temperature of my object is 200 degrees, can we predict what this what's going to happen in the future? I think you can probably guess what's going to happen, but I'd like to do that sort of in general for any differential equation without having to solve the differential equation, because that's what differential equations are good for. They're good for figuring out what the future is going to look like, based on your assumptions that you've made when you're putting the differential equation together. So let me get this here. Slope fields is the way that we're going to do it, or at least the tool that we're going to use today to do this. So a slope field is pretty straightforward. It's just you're going to place a small line. It's a graph, and you've got a little line that represents the slope at that point. Now, here's the idea, though, is just like that temperature thing, we're going to have something like this. We'll do a nice, easy one to start. dy over dx is equal to y plus x. So we have a differential equation, and we're going to put a little line on our graph. So here's our graph. Here we go. Here's y, here's x. And this gets a little bit tedious, so bear with me for just a minute. So if you remember back in multivariable calculus, we did vector fields. This is similar on a scale of tedium dealing with this. So let's go ahead and do this. At 0, 0, when y equals 0 and x equals 0, the slope equals 0. And so I will put a little slope line right there to indicate that the slope is 0. When y equals 0 and x equals 1, the slope is 1. dy over dx equals 1. When y equals 0 and x equals 2, the slope is 2. You see where I'm getting my little lines? And so I'm going to put a little line, this is supposed to have a slope of 1. This is a slope of 2. Very similar to the vector fields that we did in multivariable if you took multivariable. Let's just do a few more of these. If I move upward, when y equals 1 and x equals 0, the slope will be 1. And then when y equals 2 and x equals 0, slope will be 2. Here the slope is 2. Here the slope is 3. Things get very steep very quickly. Moving backward, when y equals 1 and x equals -1, the slope is 0 because 1 plus -1 is 0. You see where that came from. Let's put in a few more of these. So after a while, you start noticing some patterns in terms of how things are going to shake out. This is going to be like this. This is going to be like that. And then this will be like this. So anyway, pretty quickly, you can fill in a slope field diagram. This is the slope field. And all this does for us is it guides us as we want to make, if we want to give it like a good guess. It's not a perfect solution, but if you have an initial condition, for example, suppose I told you that my initial condition is y of 0 is equal to 0. So what does that mean on this slope field? It means that we're starting out right here. Well, let's follow the arrows. Just go with the flow. So as I go forward, notice that I'm going to start inching upward because as we move to the right, the slopes are going to be turning our way upward. It's going to be pushing me up because, I mean, I didn't put a slope in here, but I could have put a little slope line right there. It would be a slope of 1/2. X equals 1/2, y equals 0. Slope is going to be 1/2. And so as I move across from here, my slopes begin to go upward. Now, is this exactly what the solution curve looks like? No, but it's close. It's an approximation. It's a good guess. And you can tell from the slope lines what will happen in the future. Namely, let me just go back into the past here. There we go. That's a pretty good thing. Okay, namely, that in the future, you're going to increase without bound. So if you start here, you're going up forever. What if, on the other hand, you started right here? Y of -1 equals 0. In that case, y of -1 equals 0, starting, whoops, change color again, just a sec. There, so starting here, that paints a different picture. You get a different story. You start going downward, and there's no coming back. You just go forever. And it gets worse if you start back here. Let's say I start right here. You're actually just going down forever really quickly. So this does give us an idea about what's going to happen to a solution, for the future. So that's the idea about a slope field. Slope fields are tedious to make, but they do have a good, use. So we could make a slope field. We've already made one of like this, so I don't want to do this one. Let's see, is there a good one? Yeah, none of these are really that fun. Well, you could try this. This one's not bad. Y prime equals y squared. It's kind of interesting. So here, let's draw our little axes. 1, 2. Let's not mark those. It's going to get in the way. So you'll just have to realize that these are 1, 2, -1, -2, etc. So here's x, here's y. Go ahead and put some slope lines on here. So I guess that if we were to put all of the grid lines on here, you would have 25 slopes, wouldn't you? Because there's, let's see, 5 per line, and there's like 5 lines. But take a minute and jot down what you think the slope lines are going to look like. And meanwhile, let's see if there's another. I think there's a more interesting one coming up. Yeah, that one's more interesting. Okay. Unfreeze. All right, so yeah, this is kind of boring because there isn't an x here. And so the slopes are all going to be the same if on every horizontal line. So for example, when y equals 0, the slopes are all perfectly horizontal. So you have something like this going on. When y equals 1, the slopes are all +1. So you'd have something like this. Whoops. When y equals 2, the slopes are all 4, which is extremely steep. It's practically vertical. And then what about negative numbers? Now this is interesting. When y equals -1, the slope is positive because y prime is y squared. So these are all +1. And then these, as you go down, they're also going to be super steep. So you'd have something like this. We have a special name for differential equations like this that we'll cover in a minute, but you'll notice that like something like this is really easy because the slopes don't change as you move left and right. So it's the same slope. You can imagine extending this as far as you want left and right. You can also tell what is going to happen to a solution based on its position. For example, if you start out, if y of 0 is above the x-axis, doesn't matter how far above, let's say we start here, y of 0 is 0.2. Well, you can see that you're eventually going to increase without bound. There it goes way up there. If y of 0 starts anywhere below the x-axis, let's say you start at -2, y of 0 is -2, you're going to increase and level off right there on the x-axis. And of course, if you start on the x-axis, you just stay on the x-axis because the slopes are all 0 there. So once again, the slope field is just a tool, gives us an idea of what's going to happen in the future. Okay, one more, and then we'll change gears a little bit. So and we'll get the name of that special differential equation. But this one, so here, this one is a little bit tedious because, well, I don't know. Let's do the way I've got the grid lines set up. I have, what is that? There's going to be 81. Is that, no, that's 11 times 11, 121, 121 grid points here. That's way too many. Let's not do that many. Let's just do a few of these just to get a feel for what this might look like. So let's see. I'm going to put some dots on here that we'll do. So we'll do 0, 1. Let's see if I can find it. Here's 0, 1. That should be good. Let's do over 1 and up 2. Oh, sorry. No, that's 1, 0. My bad. Here's 0, 1. Here, we'll do both of those. 1, 2 sounds like a good one. I guess we could do 2, 2 and 1 right there. Let's go back here. We'll do this one there, and we'll do this one, 1, 1. I know it's just a sampling. We'll do a few of these just to get a feel for what they look like. So let's do this. Maybe I could make a little table over here. Let's see, t and y, and then this will be y prime. So let's see, it looks like the first one I have is -2, 2. So I'll mark them down here from left to right. -1, 2, 0, 1, 1, 0, 1, 1, 1, 2, 2. There we go. So we'll just compute the slopes. You probably could do most of these with, oh, that's really hard to read. You could probably do most of these relatively quickly without a calculator. So I'll just give you a minute and then we'll go around and you can shout out the answers when I get to you. Let me see if I can adjust the color. Color? Oh. Ooh. Oh, whoops. Sorry. Ooh. Sorry, that's hard to. I'm just going through the different. That may be the best with this green. It looks fine on my screen here. Just looks so offensive up on the. I'll just leave it alone. All right, let's see how we're doing. Adric, did you do -2 and 2? -1. So slope of -1, and So if you didn't get -1, go back and multiply -2 times 2, and then 2 minus -2. So it'll be -4 over 4. Is that right? Yeah, -4 over 4. Very good. All right, so there's my little slope field or slope line. Let's see, there's just a few more, and then I will save you from the pain here. Cooper-Stiegel, what about the next one, the -1 and 2? Very good, so -2/3, so it's negative still, but not quite as steep. Very good. And then 0, 1. See what we got there. Madison, did you get 0, 1? It's 0 because of the numerator, of course. Very nice. So that's going to be straight across. And in fact, well, let's do the next one, and then we'll talk about the in fact part. So Cooper-Claggett, what about the 1, 0? That's also 0, yeah. So in fact, everything along the x and y axis is 0, except for the origin. We'll have to talk about the origin special. We'll get there in a minute. Actually, we're going to get there right now. Yeah, so you have these slope lines. Anytime you can, exploit some symmetry or like this, where, yeah, I guess this is sort of symmetry here, recognizing that if t equals 0, the slope will be 0. If t equals 0, or if y equals 0, the slope will be 0. All right, let's deal with this 1, 1 now. All right, Caden, what did you get for 1, 1? Undefined, yeah. So this is a problem. So 1, 1 is undefined because you end up with 1 over 0. Now, the way I'm going to represent that, I guess, is going to be this. We'll just do that. Because if you did a limit from either direction, yeah, I guess it depends. Are you going upward or downward when you hit that point? That's the only question. But if you did a limit from any direction and you get closer to this point, you're going to find that that limit is going to be either positive or negative infinity. So however you cut it, either you're pointing straight up, going upward, or you're going downward when you hit that point. Okay, so we're going to just leave it like that. I'm curious, though, to see what, I've got an online tool that's going to do this for me. Okay, so that's 1, 1. I'll just, we'll just say, I'll just leave it blank there. Undefined, very nice. All right, what do we got? 2 more? Yeah, 2 more, and then we'll deal with 0, 0. Asol, what about the 1, 2? What did you get? Okay, so that one you get 2, and so here it's 2 over 1, if you did the math. So let's see, that's 1, 2, so that's a pretty steep slope. Very nice. And then 2, 1, last one. We looped around. Rachel P., what do you get for 2, 1? -2, very good. So that's almost the same calculation, only the denominator is different. So that's going down. Interesting. So it turns out that all of these points on this diagonal, because of that denominator, they're going to have this situation, except for the origin. The origin is special because the origin you get 0 over 0. So that doesn't really resolve into any slope. So I'm just going to put a dot there. And then these we could put vertical lines. So, so let's see what happens when we go to something online. I just did a Google, well, not really a Google search. I did a DuckDuckGo search for slope field generator, and this is what I got. So you can find your own slope field generator if you'd like. And on this, I could type in the function or so this, I guess it's in terms of x and y. So I'm just going to have to do a conversion here. Instead of t, I'm going to put x. So y times x over y minus x. And so there we go. All right, interesting. So they've just left this completely blank. So there is nothing going on this, which is fine. So, but you have the same sort of slopes. You can see what's going to go on in the future if you have an initial condition. Some of these slope field generators actually allow you to click a point. Whoops. Yeah, I guess there's this. This thing is movable, isn't it? Come on. Oh, maybe not. Okay. Well, anyway, I don't know what happened there. Ooh, movable point. Oh, there, it's moving. Okay, Now maybe I can grab it. But anyway, some of these will actually allow you to click a point and it'll put a solution. But you can see that with this movable point, that if you had a solution, it's probably going to go down. It's going to bottom out somewhere down here. And then, whoa, something weird happened. And then probably goes up pretty quickly. I don't know. But it'll allow you to estimate where your solutions are going. So you feel free to use something like that to help you with your homework. Okay, there we go. Okay, so last bit. Well, not the last bit. Actually, quite. First of all, this interlude. So, an idea for Valentine's Day. So, not to worry. When Valentine's Day gets closer, I will make sure that you might have had me in the past. And you might be saying, you know, I'd like a differential equations themed Valentine's card. And I've got you covered. So here's a good example. In spite of the ups and downs, regardless of the initial condition, this could be on the outside of your card. And then you could say on the inside, I love you much more today than the day we met. So you can see all of the solutions on this slope field. Okay, very nice. Yeah. Or you could have this on the outside, and then here's the slope field. I don't know if you can see what's going on with this slope field. I've got it done. I did a online. Oh wait, maybe that's another one. Yeah, I guess I get a little out of control there. Okay, so yeah, I'll make sure there's a couple of these differential equations themed Valentines that you might want to use for your special friend this year since you're taking differential equations. So I'll make sure that you have access to those. They're all, you can modify them to put your name in instead of mine. But anyway, let's go back to this. So when we get closer to Valentine's Day, I'll make sure that you get access to that stuff. So an autonomous equation, this is special. This is that the temperature thing, Newton's law of cooling, was autonomous. There were a couple of other autonomous equations that we've done today. These are special because they're easy. Autonomous equations are easier because they don't have the independent variable. Notice that this is just dy over dt is equal to some function of y. Whenever you have this, it makes things a lot easier. Let me show you what I mean by this. Taking a look at this particular autonomous differential equation. I'm not going to make you sketch the slope field because I did it for you. Watch this. If I sketch this slope field, because this is autonomous, the y is all that matters. T does not matter at all. And so, as you might expect, if you move left and right along the graph here, it doesn't matter where you are. All of the arrows look the same, moving left and right. So like here, all of these arrows, all of these, all the same. And so there's a sense in which we don't really need all of this. This whole thing is more information than we need. We could shorten or shrink this down. And so one way we could do this is sort of squeeze it down. Let's get rid of some of the extra stuff. We don't need all that extra stuff. We just need this. In fact, why don't we just get rid of everything except for the middlemost band here? That's all we really need. And in fact, what mathematicians do is we go even one step further than this, and we get rid of all of that except for the y-axis. So whenever you have an autonomous differential equation, instead of drawing that whole slope field, what we're going to do is we're going to say, what really matters are the arrows and which direction they're going. And so let's get rid of everything but the y-axis. And this is what our slope field ends up looking like. I know it might look like there's not enough information here, but bear with me for a sec. Let me just show you what I mean by this. Is I can predict, based on this, what a solution is going to do. Because I know what differential equations look like. I'm familiar with this sort of thing. Whoops, there it is. I'm familiar with this. And so all I really need to know is that there is some point up here where all of the solutions are going straight across. And then they all, if you dip down just a bit, all of the solutions dip down. And then they level off right here. And then anything down here is just going to increase and level off right there. Here, let me just show you what I mean. I'll just go back to this. So with this, because I've done differential equations before, I can predict what a solution looks like that starts right here. I can also predict what a solution looks like that starts here, or here, or here. So let me just show you what I mean by this. So the one above the y equals 4, it's just a little above y equals 4. And so I think that it will go, maybe slowly, but it will go upward, but then it will keep going up sort of exponentially. The one below y equals 4 starts out going nearly horizontal, but then it decreases and levels off around y equals 1. Y equals 1 and y equals 4, those are special points. We'll have names for them in a bit. The one that starts out right above y equals 1, it doesn't have far to go. It just pretty much drops down and sort of settles in right at y equals 1. And finally, the one below y equals 1 is going to increase and then level off at y equals 1. So we can predict the future without even solving the differential equation, just if we have a handle on the slope field. Now, let me just just show you that I'm, well, pretty much right. I guess I'm off because the 4 is no longer, my 4 for my slope, my line was here, so it's off. But you can see that everything above here slowly increases and then does this. Anything between these two, they start off and then they go down steeply and then they level off down here. And then down here, you increase and level off at 1. So this is called a phase line. And the way you draw this is pretty straightforward. You draw the y line. You identify any equilibria. So these 2 points are called equilibria. Each one is an equilibrium. So equilibria. You choose a point in each interval and compute the slope, and then you draw arrows and you're done. That's pretty much it. So this is a really nice, easy, quick way to get a feel for what solutions are going to look like. By the way, we will get, going back here, I will be able to solve this. So it's going to be painful, but we can solve that differential equation. I can give you a solution. Can I do it right now? No, I can't. Not yet. It's harder than, there's some are harder than others. This one's, it's not terrible, but it's not great. So I don't want to do it. I can't do it in my head right now, but it is something I could solve. You're going to have some exponential functions and stuff you can imagine because of all of this stuff. So, so it does have a solution, but before we get any actual solution, we could draw a phase line and we can have a feeling for what our solutions look like. So let's try this. So start with this thing. And remember, step 1 is draw a vertical line. Whoops. Okay, I guess step 1 I didn't do. Step 1, draw a vertical line. I'll do it over here. Let me change color. Step 2 is to identify any equilibria. Equilibria, those are places where the slope equals 0. So you need to solve this nice polynomial equation. In other words, can you factor that? I'll bet you can. I have faith in you. It's going to take a couple of steps, though, so don't fret. Here, I'll even get you started. Here we go. I know that's not much information I just gave you, but it'll get here. I'll even do this for you. Oh no, where'd it go? There it is. Minus plus there. Wait, no, it can't be a plus there. Sorry. There, that should, I mean, now everyone should be able to get it. But let's see. Let's find a volunteer. I know you want to show off, Luke. Luke, do you know what the factors are for this, or at least this first step? So here's a little hint. You want whatever number is right here times y to equal negative y. Okay, very good. So it's y minus 1 and y minus 3. Now, y squared minus 1 and then y minus 3. By the way, You could have done this by factoring by grouping. I don't know if you remember factoring by grouping. So take these first two here, and you factor out a y squared, and you're left with y minus 3. And then take the second two, and you factor out a -1, and you're left with y minus 3. So y squared times y minus 3, -1 times y minus 3. So there's different ways that you might go about this. Now that I've done that, now we can find the final factoring here. Whoops. Here, I don't want to give it away too much. Y minus 3. So we just have to factor that quadratic now. So take a minute and see if you can figure out the factors for that y squared minus 1. Max knows what they are, though. What are they, Max? Okay, so y minus 1 and y plus 1. Very good. So there are my factors. And now that I've got this all factored, you know what the solutions are. Hopefully you can do this yourselves. Y equals 1, y equals -1, and y equals 3. So you have the same 3 solutions? Oh, am I recording? Yes, I am. Oh, is the mic on? I'm always worried. Oh, no, it's on. Good. So we have 3 people absent, so I'll make sure that we're good. Okay, so now that I've got those, that was step 2. So step 3 was pick a point in between each pair of equilibria. So I'm going to put dots on here. This is going to be y equals -1, y equals +1, y equals +3. So I've got my 3 points. So you just have to pick any point you'd like. For example, I will pick this point, +2. So y equals +2 as my test point, and that's going to tell me whether the slopes are going upward or downward in between the y equals 1 and y equals 3. So I'll plug y equals 2 into here. 2 cubed is 8, minus 3 times 2 squared, which is 12. Now we're down to -4. Minus 2, we're down to -6, plus 3, we're up to -3. That means the slope at 2 is negative, which means that the slope everywhere between 1 and 3 will also be negative. I guess that I need to erase my arrows at the top and bottom just in case that's not the direction they're going. Okay, so you need to pick a test point in this range between -1 and 1. Plug it in and tell me if the slope is positive or negative. Pick a point above 3, and you know my favorite is to pick like 100, and then pick something less than -1. And then we're going to just compare our answers. So take a minute, get those 3 answers for us, and I will find a volunteer. All right, Zechariah, pick a point. Which one do you want to do? 0, that's a nice easy one. It's between -1 and 1. Is the slope positive or negative? Very nice. So yeah, if you can pick 0, do it. It's so much easier. Yeah, so that's going to be a positive slope. Very good. All right, you're not here to do this, but Mariah, you're here. Mariah, what would you like to pick? Okay, so that's just above the 3. So was the slope positive or negative? Okay, so positive. Yeah, I like numbers like if you pick 100, then you get like what is that going to be, 100 cubed, a million? Yeah, so that's pretty much it. You're done. Positive. Very nice. And then we need something less than -1. So let's see. Running out of people. I guess I've gotten just about everyone. Tyler, what do you want for y is less than -1? Oh, nice. And was that slope positive or negative? Okay, so here again, we'll go downward. So now we can tell what the solutions are going to do in the future. If you're close to one of these equilibria, you're going to have a horizontal slope. So let's say I start just below the positive 3. If I start right there, if that's my initial condition, the slope will start off pretty much 0, but it'll slowly decrease until it gets really steep. But then you'll hit this like level place here because you can't cross that equilibrium. And so it'll level off eventually. Let me just show you on, what is this? The one that I picked, the Desmos. Desmos, let's crank this into Desmos just to see how Desmos makes this look. Give me a sec, get rid of all of this. So I have y cubed minus 3 times y squared. Does it like me? Sure. Minus y plus 3. Did I do it? Yeah, there we go. I don't really like this. Can I zoom in? I'm sure there's some setup I can do. I'm not thrilled with this. But this is the slope field. So you can see those equilibria. This is -1, +1, +3. In between +3 and 1, you have these decreasing. Yeah, there must be a way to set this up. Just a sec. Let's see. The slope grid. 21 element list. Oh, I don't know. I probably would have to do some work. I don't know how to make the slope grid different. So we're just going to ignore it. Is there a setup here? Okay, yeah, I don't care enough. Yeah, but I'm sure that you could figure out how to make the grid like have more slope lines so that we can see the nice curve here. So, or if I found a different, let's see, you can see what I did. Let's back up. Yeah, leave that page. Go away. There we go. See? DuckDuckGo, slope field generator. I just took the first one. GeoGebra apparently has one. I know some of you love GeoGebra. So there's other ones here. So, but if you need help with some of that. Okay, let's see. What else do we got here? Give me a sec. How much time? We got 10 minutes? Let's see. Yeah, let's just do one of these. Nah, we'll do 2 of them. Here we go. Do this. So, yeah, this one's kind of cool. Let's do this one. That one's cool. And then if we have time, we can do one of the more boring ones. So dy over dt is y times sine of y. I want to find the slope field or the phase line for that. So y times sine of y. Let me write it down over here so that we can enjoy it together. Here we go. So dy over dt is y times sine of y. I'll get it started here. Look at this. I've got a nice, oops. I don't want to put the arrows on there. Let's just make a vertical line. So you need to find the equilibria. Set this equal to 0. Find out where this it has a horizontal slope. Oh, did I mention this is called an autonomous? I think I might have autonomous. I don't know if the book, if it's, just in case, autonomous means no t's or x's in the differential equation. Autonomous. Someone made an appointment with me. Oh, well. All right, let's restart the randomizer because I think I've hit almost everyone. Someone's not here. Oh, but Cooper Stiegel's here. Cooper, can you tell me at least one of the equilibria? Yeah, y equals 0. Nice, easy one. So if you do this, you say, oh, look, y equals 0 or sine of y equals 0. Okay, let's deal with the sine of y. So here's y equals 0. Nice. Now let's do the sine of y equals 0. Does anyone know offhand when sine of y equals 0? Oh, that's right. Multiples of pi. Every multiple of pi, including 0, by the way. So you have pi, 2 pi, 3 pi, and some dots there because we get tired. And y equals negative pi, y equals negative 2 pi, and some more dots. Okay, we're going to have to do a little bit of work here, but I think we're up to the task. I think we're good. So check this out. I'll do the first couple. Let's pick a point in between y equals 0 and y equals pi. You can pick whatever point you want. I'm going to pick the point pi over 2 because I happen to have in my head what the sine of pi over 2 is. Sine of pi over 2 is 1. And so when I plug that in here, I get pi over 2 times 1, which is pi over 2. But the important thing here is that that is positive. Let me do one more for you, and then I'll see if you can do one. The next one I'll do is this one up here. Between pi and 2 pi, I happen to know the sine of a bunch of angles, but an easy one is 3 pi over 2. 3 pi over 2 has a sine of negative 1. So when I plug 3 pi over 2 into this expression, I get 3 pi over 2 times negative 1, which is negative. So that'll be a negative slope. By the way, I'll do this one as well. That's going to be positive. Okay, so pick a point between 0 and negative pi. Do you happen to know offhand any of the angles in there and their signs? So does someone want to show off? You don't have, it's okay. It's not really showing off. It's just getting, which one? Negative pi over 2? Is that what you said? Okay, so what is the sign of negative pi over 2? Negative 1. So if I plug negative pi over 2 into this, I have negative pi over 2 times negative 1, which is positive pi over 2, which will be a positive slope. So if you thought that these were just going to alternate, you're not quite right. They're the same here, but they do alternate down here. If you pick negative 3 pi over 2, you get positive 1, and that times a negative number gives you a negative slope, and so on and so forth. So that's what that's going to look like. All right, very nice. We're going to stop it there because I got to go see someone. Apparently, someone decided they had a meeting with me. On the homework, right now it just says page XX because I was too lazy to look up the page number, but it's section 2.1. No, it says section 2.1. I'll fill in the page number next time I'm sitting down with my book. So I think I've got it all set up. I'm going to double check before I go. I'm also going to stop the recording so that no one can hear you whisper to me.